Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Algebra 1 and II class. Today we'll be learning about how to find the nth root of a number and also about rational exponents. Okay? But let's first talk about finding the nth root of a number. If I have the equation a to the n power equals b, with a and b as real numbers, and n is a positive integer, n being the exponent, then a is an nth root of b. For example, 2 to the third power equals 8. So what that means is that the cube root of 8 is 2. Why? Because this power relates to the index. They're opposites, okay? The root of a number is basically trying to answer the question, what number times itself that many times gives you the value inside of the radicand? And the answer to that question is the base of the original exponent. If n is odd, okay, if n is odd, there is one real nth root of b, denoted in the form as the nth root of b. There's only one. If it's odd, it's either positive or negative. The cube root of 8 is 2, because 2 times 2 times 2 is 8. The cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So if n is odd, you're only going to have one real root. It's either going to be positive or negative. However, if n is even, okay, if the index is even, when b is positive, there are two real nth roots of b. There's the positive root, which is the principal root, or the principal nth root, and its symbol is simply the nth root of b. Or the negative root is its opposite root, or negative nth root of b. When b is negative, there are no real even roots. When b is negative, there are only real roots for odd indexes. You can use a radical sign to indicate a root. The number under the radical sign is called the radicand, and the index gives the degree of the root. So we saw this yesterday, but just to refresh your memory, this is the root. This tells you how many times do I have to multiply a number by itself in order to get the inside value, which is called the radicand. And the actual symbol here is called the radical sign. Please remember that if there is no index, then it is a square root. The index equals 2 when it's blank. It's invisible. If n is greater than or equal to 2 and even, then a and b must be greater than or equal to 0. You cannot have radicands that are negative inside of even roots. Okay, those are not real numbers. If the index n is greater than or equal to 3 and odd, then a and b can be any real number, period. You can have negative radicands inside of odd roots. When you're finding the real roots of a number, use the index to determine how many values are needed to pull out one of that value. So for example, The cube root is 64. You can break this down if you had to, okay? And every set of 3 of the same numbers comes out as one value. So if I go ahead and start breaking down the cube root of 64, most people are going to say 8 times 8. And then this is going to be 4 times 2. And then this is going to be 4 times 2. Circle the primes. And then this 4 breaks down into 2 times 2. And then this 4 breaks down into 2 times 2. And that's it. I'm left only with prime numbers. Remember, in this case, you look at, in all cases, you look at the index for however many sets of numbers that are equal to the index, you pull them out as 1. So in this case, I'm looking for sets of 3. So a 2, and a 2 comes out as a 2. A 2, and a 2 comes out as a 2. So my answer here is 4. Because 4 times 4 is 16, times a third 4 is 64, and the cube root of 64 is 4. Okay? What are the real cube roots of the following? So let's say I have a cube root here of 0.008. Well, ignore the decimals for a second. Hopefully by now you remember that the cube root of 8 is 2. But there's 3 decimal points. So this is going to be 0.2. Because 0.2 times 0.2 times 0.2 is 8. But I have 3 decimal points, so I got to go 3 to the left, rendering me with the radicand of 0.008. The cube root of negative 100. You can have a negative radicand for odd roots. And in this case, it's going to be negative 10. Because negative 10 times negative 10 is positive 100, times a negative 10 is negative 1,000. The cube root of 1 over 27. When you have a fraction like this, you can split them up. So I can have the cube root of 1 over the cube root of 27. And the cube root of 1 is 1, and the cube root of 27 is 3. And you're golden. Done. For example, 2. What are the real 4th roots of the given examples? Well, the 4th root, now we're asking what number times itself 4 times gives me the radicand. Well, the 4th root of 1 is just simply 1. What's the 4th root of negative 0.0001? A lot of you will be tempted to say negative 0.1, but no. There are no real roots. None. Sorry. No real roots here. Because you cannot have negative radicands inside of even roots. Okay? This is a value, but it's a complex number. It's an imaginary number. It's not a real root. As far as the 4th root of 16 over 81, well, I have the 4th root of 16. Remember, I can split these up over the 4th root of 81. The 4th root of 16 is going to be 2. Because 2 times 2 is 4, times 2 is 8, times 2 is 16, so that's a 2. Okay? However, 2 has an absolute value attached to it because it has an exponent of 1. And remember what we said. If you ever take out an odd root from an even index, it has to be an absolute value. And 81 is going to be 3. The 4th root of 81 is 3 because 3 times 3 is 9, times 3 is 27, times 3 is 81. So it's 3 to the first power. So that's an odd root coming, or odd exponent coming from an even root. So that's an absolute value. So my answer is 2/3 as well. Check out example 3. Let's do a few more. The cube root of 8, that's 2. We don't have to worry about putting odd indexes in absolute value ever. We only have to worry about the absolute value when it comes to even roots. The square root of 0.04 is 0.2. But that has an exponent of 1, so it must come out as an absolute value, which equals 0.2. The fourth root of -1, that's not a real root. Now, the square root of -2 squared, remember what we had talked about? I can cancel this root out with a power of 2, leaving me with a -2 here, but that has an exponent of 1, so it has to come out as an absolute value, which is going to equal 2. Another way to look at this is as follows. -2 squared is going to be the square root of 4, which is 2 as well. Okay? And that 2 also has to be an absolute value, which equals 2. The cube root of -27 is -3. Because -3 times -3 is 9, times a -3 is -27. The fourth root of -8, it's not a real root. It's imaginary. We'll get into that later, but for right now, that is not a real root. And that's what I was asking for, the real roots. Okay? Now, for any real number a, the nth root of a to the n power will equal a if n is odd, and it will equal the absolute value of a if n is even. Again, I'm repeating myself here, but I want to make sure you get this. In other words, when you take out an odd exponent from an even root, it must be an absolute value, period. The cube root of a cubed, that equals 1. No worries. But the square root of a squared will equal the absolute value of a. Whenever I take out an odd exponent from an even root, it must be an absolute value. Okay? Let's work on these. Square root of 16x to the 8th. Okay, remember there's an invisible 2 here, so the square root of 16 is 4. The square root of x to the 8th, remember that we divide the variable's exponent by the index. In this case, there's an invisible 2. So this is going to be x to the 4th. Done. Now, some of you may say, wait. Don't we have to put that in absolute value? No. You only have to put numbers and variables in absolute value if you pull out an odd exponent from an even root. But in this particular case, actually, 4 should have been an absolute value to be technical. So it would be 4x to the 4th. B, the cube root of a to the 6th, b to the 9th. It's going to be a cubed, b cubed. No need for absolute values when you're talking about odd indexes. And actually, Mr. Moore needs to learn how to divide. This would be a squared b to the 3rd. Sorry about that, because 6 divided by 3 is 2. 9 divided by 3 is 3. For C, I've got the fourth root of x to the 8th, y to the 12th. So that's going to equal x squared, y cubed. Since I pulled out an odd exponent from an even root, the y cubed must be an absolute value. The cube root of -2/3 to the 6th, a to the 12th, b to the 15th. Okay, first of all, this negative, treat that like a -1. And the cube root of -1 is simply -1. The cube root of 2/3 to the 6th, 6 divided by 3 is 2. So this is 2/3 squared that gets pulled out. A to the 4th, b to the fifth. So in the end, when I simplify it, it's going to be negative 4/9 a to the fourth b to the fifth. No need for absolute value because we're working with an odd root. 81x to the fourth. This is going to be 9 in absolute value because the exponent of 9 is 1. When I pull an odd exponent out of an even root, it must be an absolute value, times x squared, which equals 9x squared. The fourth root of x to the 12th, y to the 16th. This is going to be x cubed in absolute value, y to the fourth. Why did I put the x cubed in absolute value? Because I pulled out an odd exponent from an even root. Okay? Hopefully this is making sense, my friends. Now, you can write a radical expression in an equivalent form using a fractional or rational exponents instead of a radical sign. In general, the nth root of x equals x to the 1 over n for any positive integer n. Like the radical form, the exponent form indicates the principal root. So the square root of 36 can be rewritten as 36 to the 1/2. The cube root of 64 can be rewritten as 64 to the 1/3. The fourth root of 16 can be rewritten as 16 to the 1/4. Okay? Now, how does it work completely? Well, if I just have x to the 1 over n, it's simply the same thing as saying the nth root of x to the first power. The numerator of the rational exponent is the exponent of the radicand. And the denominator of the rational exponent is the index. It's a little clearer here in the second example of x to the m over n. X to the m over n can be written as the nth root of x to the m. The numerator of the rational exponent is the exponent of the radicand, and the denominator of the rational exponent of the exponent, is the index. Or you could say the following: the nth root of x raised to the m power. You could do either one, whatever makes it easier for you. I like this one. Some people like this one. It doesn't really matter. Okay, now, what have I said? X to the negative m over n. Remember that we can't have negative exponents. So to make them positive, we got to bring it down to the denominator. So x to the negative m over n really equals 1 over x to the m over n, which equals 1 over the nth root of x to the m power. Remember that the numerator of the exponent of the rational exponent is the exponent of the radicand. The denominator of the rational exponent is the index, or the root. Okay, let's convert each into a radical form. X to the 3/7 is the 7th root of x cubed. Y to the negative 3/5. What I'm first going to do is I'm going to say, okay, this is y to the negative 3.5, which is really to the negative 7/2, right? Which equals 1 over y to the 7/2, which equals 1 to the square root of y to the 7th. Which then I can further simplify, right? I could turn this into 1 over 7 divided by 2 is 3. So the absolute value of y cubed times the square root of y, because you had 1 left over. Why did I put the y cubed in absolute value? Because I took out an odd exponent from an even root. W to the negative 5/8 would equal 1 over w to the 5/8, which would equal 1 over the 8th root of w to the 5th power. And y to w to the 0.2 is the same thing as saying w to the 2/10, or even better yet, w to the 1/5, which would equal the 5th root of w to the 1st power. Okay, it seems a little confusing at first, but I promise you will get the hang of it. So let's remember, x to the 1 over n is the nth root of x to the 1st power. X to the m over n is the nth root of x to the m power, or the nth root of x, all of it raised to the m power. And x to the negative m over n equals 1 over x to the mn, which equals 1 over the nth root of the square of x to the m power. Sorry, 1 over the nth root of x to the m power. Now I want you to convert these into exponential form. Well, the square root of a to the 5th is going to be a to the 5/2. Remember that the index is the denominator and the radicand's exponent is the numerator. This 5th root of y raised to the 4th power would be y to the 4/5. The 4th root of x cubed would be x to the 3/4. The 5th root of b on all of it cubed would be b to the 3/5. Okay? Almost done, guys. Next, let's go ahead and find out what is each number in simplest form. Okay, this is 16 to the negative 2.5. So really this is 16 to the negative 2/5. I'm sorry, my bad. 16 to the negative 5/2. My bad, pay attention. Which really equals 1 over the square root of 16 to the 5th. However, I have 5 sets of 16. Okay? 5 divided by 2, I can pull out 2 of those sets of 16. So I've got 1 over 16 squared times the square root of 1 more 16 left, which will equal 1 over 16 cubed. What did I do there? I'm sorry. Wow, messed up bad. 1 over 16 squared times 4. Because the square root of 16 is 4. Okay? So let's go over that again. I have 1 to the negative 5/2, which equals 1 over 16 to the 5/2, which equals 1 over square root of 16 to the 5th power. 5 divided by 2 is 2. So I can take out 2 sets of 16. So I've got 1 times 16 squared times 1 square root of 16 left over. And the square root of 16 is 4. So that will equal 1 over 16 squared times 4. And now 16 times 16 is 256 times 4. So that would equal 1 over 1024. Okay? I've got negative 32 to the 4/5. Well, this is the 5th root of negative 32 to the fourth power. I have no worries here that it's going to be negative because I have an odd index. Now, what sometimes people do is they say 32 and then they raise it to the fourth power and then they start breaking it down from there. I don't like to do that. I like to do it as such. First of all, if I multiply negative 32 times itself 4 times, I'm going to get a positive answer. So I'm going to break this down to 32 times 32 times 32 times 32. Let's see what 32 breaks down into. This is 16 times 2. This is 2 times 8. This is 2 times 4. And this is 2 times 2. So if you notice here, I've got 1, 2, 3, 4, 5 2's. So every 32 is really composed of 5 2's. And am I not dealing with a fifth root here? So I can, for every 5 sets of the same value in a fifth root, I can pull out one of those numbers. So I can pull a 2 out for this 32, and a 2 for this guy, and a 2 for this guy, and a 2 for that guy. So 2, 4, 8, this will equal 16. It's a lot easier than multiplying 32 times itself 4 times and then trying to break that down. A lot easier. 32 to the negative 3/5. That equals 1 over 32 to the positive 3/5, which equals 1 over the fifth root of 32 cubed. Well, we know that 32 already, the fifth root of 32 is 2. So 2 cubed would be 1 over 8. 9 to the negative 3.5. Negative 3.5, that's 3.5. So that would be 7 halves. So this is 9 to the negative 7 halves, which would equal 1 over 9 to the positive 7 halves, which would equal 1 over the square root of 9 to the 7th. But the square root of 9 is 3. And aren't there 7 sets of 9s? There's 7 9s. So 7 sets of 3 would be 1 over 21. Okay? Now, let's get fun here. This is where we have some awesome times here. Okay. If you guys remember your power of exponents, you multiply, when an exponent is raised to a power, you multiply it to everything. Okay, so you're going to multiply this 2/3 to this and that. So I've got negative 8, okay, the cube root of negative 8 squared. Well, I'm going a little bit advanced here. Hold on. This would be negative 8 to the 2/3, x to the 2/3, and I'm going to convert this square root into a 1/2. So this is xy to the 1/2 times 2/3. So this is going to give me the cube root of negative 8 squared of x squared. These two cancel, so I'm left with the cube root of another xy. This is going to give me the cube root of 64 x cubed y, and the cube root of 64 is 4. The cube root of x cubed is x, and I have a cube root of y left over. If you need to see that again, hit rewind and watch it again. I have 16y to the negative 8th raised to the negative 3/4. So I'm going to distribute this exponent to everything inside of the parentheses, giving me 16 to the negative 3/4 times y to the negative 8th raised to the negative 3/4 power. So this is going to give me 1 over 16 to the 3/4. I want to make my life easy here. 4 goes with the negative 2 times. So this is times y to the 6th power, which is going to equal 1 over the 4th root of 16 cubed times y to the 6th, which is going to equal y to the 6th over the 4th root of 16 is 2, and 2 cubed is 8. Okay, 8x to the 15th raised to the negative 1/3 power. Distribute this to everything here. It's just going to be 8 to the negative 1/3 times x to the 15th raised to the negative 1/3. So this gives me 1 over 8 to the 1/3 times x to the negative 5th, which equals 1 over the cube root, the cube root of 8 times 1 over x to the 5th, which equals 1 over x to the 5th times the cube root of 8. Okay? And we're going to see later how to do something called rationalize that. You're not really supposed to have radicals in the denominator, but we're going to walk before we run. Okay, 9x times the 4th root of y raised to the 3/2 power. Everything here gets multiplied by 3/2 exponent. So I have 9 to the 3/2 times x to the 3/2 times, remember that the 4th root of y is y to the 1/4 times 3/2. This is going to give me the square root of 9 cubed x cubed times the 8th root of y cubed. How did that work out? Because here, this is y to the 3/8. So, the square root of 9 cubed, I can take out, a square root of 9 is 3, right? And 3 cubed is 27. So absolute value of 27, because I took out an odd exponent from an even root. The square root of x cubed, I've got another absolute value of x, and I've got a square root of x left over, and then I have times the 8th root of y cubed. So when we put it all together, nice and pretty, we've got 27 times the absolute value of x times the square root of x times the 8th root of y cubed. That's a good one. Okay? I know this is kind of crazy, guys, but I know you can do it. So just take your time, rewatch the video if you have to. And last but not least, let's evaluate each of the following expressions if possible. Okay. 5 to the 3/2. This is the square root, 25 to the 3/2. This is the square root of 25 cubed. Don't make a mountain out of a molehill here. The square root of 25 is 5. 5 cubed is 125. 64 to the 2/3. This is the cube root of 64 squared. The cube root of 64 is 4. 4 squared is 16. The square root of negative 9 to the 5th power. This will not be a real number. This is not real. Because when I multiply negative 9 times itself 5 times, it's still going to be negative. So that will not work. Negative 8 to the 4/3. This is the cube root of negative 8 raised to the 4th power. The cube root of negative 8 is negative 2. Negative 2 to the 4th power, 2, 4, 8, 16. So this would equal positive 16. Negative 81x to the 7 halves. This is the square root of negative 81 to the 7th times x to the 7th. But when I multiply negative 81 7 times by itself, it's going to give me a negative, so this is not real. And last but not least, if I have 1 over 8 to the negative 2/3, that's the same thing as me saying 8 to the positive 2/3 up here in the numerator. I brought it up, which is the cube root of 8 squared. The cube root of 8 is 2. 2 squared is 4. I know this is a heavy lesson. Take your time with it. Thank you very much. I hope you learned a lot. Rewatch it if you have to. And thank you. Have a great day. Bye-bye.